Hello friends, subscribers and new viewers of this channel. In this tutorial we explain how to design and simulate observers of dynamical systems in Simulink. We will also perform some basic calculations in MATLAB, however the main workhorse in this tutorial is Simulink. Here is a brief summary of what you will learn in this video tutorial. First, we will briefly go over the foundations of observers. We will explain what is observer, how the observer is being designed. Then, at the end, we will introduce a simple system that's shown over here and that's used to verify the performance of the observer. As a test case in this tutorial, we will consider a double mass spring damper system shown over here. We assume that only the position of the first mass can be measured. And this is a very important constraint that enables us to truly test the performance of our observer. Namely, the goal of the observer will be to reconstruct the complete state of this mass spring damper system that consists of 4 state variables by only measuring a single state variable. And by analyzing this example and by implementing in MATLAB, you will start to appreciate the power of observers. By the end of this tutorial, you will be able to implement the Simulink block diagram that implements the plant dynamics, that is, the dynamics of our mass spring damper system, and that also implements the observer that you can see over here. Then you will be able to run the simulations by clicking here and to show that actually the observer can track the state of the system. Namely, over here, you can see this yellow line. This yellow line represents the state of the observer, and the blue line represents the state of the plant. We can see that approximately after 2 seconds, the observer is able to accurately track the state of the system. That is, you will be able to design a convergent observer that's asymptotically stable, meaning that the estimation error will converge to 0. Also, a link to the developed MATLAB and Simulink codes will be provided in the description below this video. Okay, let's immediately start. We consider linear dynamical systems represented by this state space model. Over here, X is the state, U is the control input, Y is the observed output or the measured output, and A, B, and C are the system matrices, and X dot is the first derivative of state. We can represent the system by this block diagram where the input arrow represents the input U and the output arrow represents the output Y. That is, it represents the observations. Here, it should be emphasized that only the output vector Y of this system over here can be observed or measured. However, in many applications, we would like to have access or information about the full state vector X. For example, in order to design a state feedback control algorithm, we need to have information about the state vector X. There are also many other scenarios in which we need information about the full state vector X. This motivates us to develop an algorithm, or better to say an estimator, that will estimate the state vector from the sequence of the observed output vector Y. Such an algorithm is called an observer in the control engineering literature. The main goal of an observer is to estimate the state of the system from the measurements of the output vector. And over here we also have to mention that we need to have the knowledge of the input vector. Also, it should be emphasized that when designing the observer, we assume that the system matrices A, B, and C of this state space model are known. Under this assumption, the observer of the system is actually given by this equation. And here is again the observer equation. Over here, L is the observer gain matrix, Y is the system output, C is the output matrix, X hat is the state of the observer, and this is very important to keep in mind. And A and B are system matrices of the plant, u is the control input vector, and this equation actually represents the dynamics of the observer. This equation can be discretized and implemented in hardware such as FPGAs, microcontrollers, etc. Over here, it's very important to observe the following. The hat notation over here denotes the state of the observer that is at the same time an estimate of the system state x. That is, you should distinguish between x, the state of the system, and x hat, the state of the observer. This is very important to keep in mind. X hat is the state of the observer, this is not the state of the system, and x is the state of the system. The matrix L is the observer gain matrix. Our goal is to design this matrix such that the state of observer state, or better to say x hat, asymptotically tracks the state of the system. Again, our goal is to design the matrix L such that the state of the observer x hat asymptotically tracks the state of the system x. Or equivalently, we want to design the observer gain matrix L such that the state estimation error, that's denoted as the difference between x and x hat, asymptotically approaches zero. As we will explain and see later on, this means that the closed loop observer dynamics has to be stable. Here's a block diagram of the real physical system and the observer. Note over here that the state x of the real physical system is usually not known. All we can know about the real physical system is its model, that is, the system matrices A, B, and C if the system is linear. Otherwise, if the system is nonlinear, we will have to linearize the system around certain operating point, and then we can extract A, B, and C system matrices. However, that's another story. Now, what we can extract from this system? We have sensors over here, and we can extract the outputs, that is the measurements, and at the same time we know what are the control signals that we are actually sending to the system, that is, we know U. So observer, that is this block, takes input U and the output Y as its inputs and spits out, or it calculates x hat. This is very important. So what is an input of the observer? The input of the observer is the control input of the real physical system and the observed output of the real physical system. To repeat, the inputs of the observer are the real control input, that is the control input of the real system, and the observed output of the control system. And the output of the observer is its state, x hat. Again, I mentioned this previously and I will repeat since this is very important. You can discretize this observer equation and you can implement it in your FPGA or microcontroller in a simple for or while loop. It's very simple. Okay, now our main task is to design the system matrix L such that the state x hat over some time, or let's say over certain predefined time, accurately approximates the state of the real system. Or better to say, x hat should accurately estimate the state of the real system. How to design observers? That is, how to design observer gain matrix L. First of all, we start from the observer equation. Here it is. Then we introduce the estimation error. The estimation error is a difference between the state of the real system minus the state of the observer x hat. Then, if we differentiate the estimation error, we will obtain the third equation. Then, if we substitute the system dynamics in the third equation, we obtain this fourth equation, that is, we obtain ax plus bu instead of x dot. Then, instead of x hat dot, we can simply substitute the observer dynamics. That is, we will, instead of x hat dot, obtain minus x hat minus bu minus l multiplying y minus c x hat. Then, if we proceed further and we rearrange the terms and cancel BU and BU, we obtain this equation, and further we go, then we can further eliminate, group things together, and finally we obtain the last equation that E dot is equal to A minus LC multiplied by the estimation error. And if we further proceed, instead of x minus x hat, we can write simply the estimation error, and we obtain the closed loop observer error dynamics. Here it is. E dot is equal to A minus LC E. That is, control inputs are eliminated, the states are eliminated, the states of the observer eliminated. We only have pure error dynamics. Now, the goal is to design this matrix cell such that the closed loop observer error dynamics is asymptotically stable. What does it mean to asymptotically stable? This means that for any initial error in estimation, the error over time will approach zero asymptotically, and this means that over time x hat will become x, and our observer will be able to accurately estimate the system state. So how do we find the matrix L? We simply can use the pole placement method to select the poles of the matrix A minus LC. And in MATLAB, we will do it by using the place function. So here is the goal for our simulation. First of all, we are going to pick a test example. Our test example is going to be a mass spring damper system. Then we will write a state space model, then we will design the matrix L, and then we will simulate the complete system in Simulink. So let's start. Here is our test example. We consider a system composed of two boxes where the masses of boxes are M1 and M2. Then we assume that the boxes are connected by a system of springs and dampers. D1 over here is the damping constant of the first damper. K1 is the spring constant of the first spring, D2 is the damping constant of the second damper, and K2 is the spring constant of the second spring. S1 is the displacement of the first box from its equilibrium position. S2 is the displacement of the second box with respect to its equilibrium position. F is the control force that acts on the second box. In this particular example, we assume that we have a sensor measuring the position of the first box. That is, we assume that we can measure the position S1. And that's the only output that we can extract from the system. Now, the next step is to derive the state space model. To derive the state space model, first of all, we need to write differential equation describing the dynamics of this system. This differential equation is obtained by applying Newton's second law. After obtaining that equation, we can introduce the state space variables. And the state space variables are x1 is equal to s1, x2 is equal to s1 dot, x3 is equal to s2, and x4 is equal to s2 dot. That is, x1 is the position of the first box, x2 is the velocity of the first box, x3 is the position of the second box, and x4 is the velocity of the second box. We group all the state space variables in the vector x, and the input u is the force F acting on the system. The state space matrices are given over here. The A matrix has this form over here. In this A matrix, K1 and K2 are the spring constants of the spring 1 and 2. M1 is the mass of the first box. D1 and D2 are the damping constants of the two dampers, and M2 is the mass of the second box. You can see how the B matrix looks like, and the C matrix is 1, 0, 0, 0. This means that we are only measuring the first state, that is, we are only measuring S1. And our goal is to design the observer for this system and to simulate it in Simulink. Before I start with code development and with implementation of the code, I need to mention the following. A link to all the code files presented and developed in this video tutorial, as well as to Simulink files, will be provided in the description below this video. Okay, so let's start with coding. Before we can actually develop a Simulink model, it's very important to implement and to define all the system parameters in a MATLAB script. First of all, we are going to define the state space matrices, then we are going to compute the matrix L, and then we will switch to Simulink. So let's start. First of all, let's clear everything and let's define the masses. So here I'll just type system parameters and let's start with masses. So I will assume that the mass 1 is 5 kilograms, mass 2 is 10 kilogram, spring constant K1 is, for example, 50, spring constant K2 is, for example, let's say 80, then damping D1 constant is 5, damping D2 constant is, for example, 3, and let's define our A state space matrix. Here it is. It's 0, 1, 0, 0. This is the first row. Then in the second row we have minus K1 plus K2 divided by M1. Then we have the following. We have minus D1 plus D2 divided by M1. Then we have K2 divided by M1. Then we have D2 divided by M1. And let's nicely write everything. Let's put tabs such that we know what we are typing. Good. Then let's start with the third row. The third row is very easy. It's 0, 0, 0, 1. And the last row reads as follows. We have K2 over M2. Then we have D2 over M2. Then we have minus K2 over M2. And finally we have minus D2 over M2. So let's verify everything. Let's see 0, 1, 0, 0, minus K1 plus K2 over M1, minus D1 plus D2 over M1, K2 over M1, D2 over M1, 0, 0, 0, 1, K2 over M2, D2 over M2, minus K2 over M2, and D2 over M2. Good. Let's continue with B matrix. The B matrix is going to be 0, 0, 0, and 1 over M2. C matrix is going to be 0, 0, 0, and D matrix is going to be empty. Over here, just for verification, I will compute the step response of the system. Let's do that. I will define system 1 is state space A, B, C, D, and let's see what is step of S1, system 1. And let's see the response. Let's select this and let's evaluate this selection. And let's hope that everything is fine and that we have a reasonable response of our system. Okay, so it looks good. Right. The response is not very well damped, however it makes sense. The system is stable as expected and it settles, for example, after 40 seconds. Good. Let's continue. Next, we need to determine the matrix L such that the matrix A minus LC is asymptotically stable. To do that, we will use the pole placement method. That is, we will first specify the desired pole locations and then we will use the MATLAB's function place to design the matrix L. So let's do that in MATLAB. First of all, let's define desired pole locations. Okay, so I will put them like this: pole location and desired. Let's call it like this. I will put one pole at -4, another pole at -6, and then I will have two imaginary poles. For example, -2 plus 2i and -2 minus 2i. We can see over here that all the poles are strictly in the left half of the complex plane. This means that our matrix will be stable. Now, to apply the pole placement method, we need to use the MATLAB's function place. So let's type help place and let's see what this function is doing. They're saying this. Place computes a state feedback matrix K such that the eigenvalues of A minus BK are those specified in the vector P. In our case, the vector P is actually this pole location desired, right? However, the issue over here is that we have A minus BK. However, in our case, we have A minus, and let's see again, L times C. Okay, A minus L multiplying C. So there is an issue here, right? And what this function is actually doing, it's assigning the poles of B times K. That is, the K is the matrix that will be determined. This is a state feedback matrix. However, in our case, we have something like this. So how to resolve this problem? Well, we can resolve this problem relatively easily. So instead of doing the pole placement of A minus LC, we can simply transpose the complete matrix, and then we will do the pole placement of A minus C transpose multiplying L transpose. And then what will happen? The function place will actually return the matrix L transpose, and then we will use that matrix by simply transposing it, and we will obtain our matrix L. So let's write it down. Okay, so we will type this. LT, standing for L transpose, we simply place, and we will do A transpose, C transpose, and then we will simply specify pole locations desired. That's it. And then we will say at the end, once this is computed, L is equal to LT transposed. And then later on we will verify the eigenvalues and make sure that everything is okay. So let's evaluate this and let's see the output. Okay, here it is. Again, let's close this window and let's see what's happening over here. So okay, here's our matrix L. Sounds good. However, let's do one final check. Let's compute A closed loop is equal to A minus L multiplying C. This is actually our closed loop matrix. And let's verify, that is, let's check the eigenvalues of this matrix, ACL, and the eigenvalues should actually be the desired poles specified over here. So let's do that and let's verify this. And over here, oops, I didn't evaluate this. We should see. Good. Let's compare now what is written here and what are our desired poles. Here is minus 4 plus 0i, perfect. Minus 6, I see this one, and then I see these two imaginary poles. Perfect. This is exactly what we wanted. Now we have the matrix L, and we can proceed to Simulink. That is, we have everything to simulate our system in Simulink. Before we actually start Simulink, let's evaluate again everything. That is the whole script. And all the variables over here will be in MATLAB workspace, and Simulink will be able to access them. That is, the Simulink will be able to access A, B, C, D, and the matrix L. This is what we want. To start Simulink, you simply need to type Simulink over here, and the Simulink will be started. Let's start with the blank model. And here you need to be patient. Okay, so this is our empty Simulink model, and we can start with modeling. The first step is to implement our state space model. So let's do that. We need to implement this state equation. X dot is equal to AX plus BU, and Y is equal to CX. Now, in order to simulate this state space model in Simulink, we need to rewrite our state equation like this. The state equation can be written like this. We can simply say that X is an integral of AX plus BU, and over here the integration is performed with respect to time. And Y is CX. Once we have this form, we can actually implement everything in Simulink. So let's do that. Okay, first of all, let me close this, or let me keep it open such that we can see it. We need to add an integrator. So double click over here and search for an integrator. integrator. Okay, so here's the integrator. This integrator will correspond to this integration operation over here. The output of this integrator is obviously our state x. Okay. The input to this integrator is this sum. So let's create this sum over here. First of all, we need to click here and search for sum. So add the sum over here. The output of this sum goes into the integrator, which is very important. On this side, that is, we will have A multiplying x. So let's create a matrix. We can perform matrix multiplication in Simulink using several approaches. In my opinion, the easiest approach is to use a gain. So double click here and search for gain. Click on the gain, then click here. Then over here you can click on format, and let's rotate this gain like this, and let's enlarge this gain. Double click on the gain, and over here we're going to specify A. And you can see that Simulink is able to automatically recognize our A matrix from the base workspace. This is very important. This is because the script is evaluated and all the variables, that is all the matrices, are in the MATLAB memory. Here you need to adjust multiplication. This should be matrix multiplication, and click OK. The output of this integrator is our x, and now we have over here A multiplying x. And we can simply, for example, type here x, such that we know this is the state. Then this part goes in this summation port, and now we have ax. Good. However, we need bu. Over here, for simplicity, I will assume that u is a constant. So type here and search for step, and click here. And this is our step function, which will represent an input. Double click here, put the step time to be 0. Then over here, we need to specify this matrix B. Again, double click, search for gain. Here it is. Double click here and put here B. And you can see that Simulink is able to access B from MATLAB workspace. But however, I made an error. Be very careful what happened. So I forgot to specify here that it's a matrix multiplication. All the scalar and matrices in this case are the same. So you can also use element-wise. However, stick to this. This is very important. So again, double click to verify. B and multiplication is matrix. Click here, connect this port over here, and connect this part over here. Now we have here B multiplying U. Here it is. Let's just put here that this is U, and this is B multiplying U. This is actually AX. You can simply type it here, AX. Here is BU. Okay. Now we sum them together. We obtain this sum, we integrate, and we obtain X as the output. However, let's put our output over here. So where is our output? Well, to create the output, we need to add a gain. So type gain here. And over here, you need to specify the gain should be C matrix. Now we are modeling the output equation. And over here, make sure that it's a matrix. And here it is. Bang. Good. And now over here is the output. To see the output, let's click over here and search for scope. And let's put a scope. Let's put it here. Perfect. Now we have everything and we can simulate our system. To simulate the system, simply click here and click on run. And let's see what will happen. However, there is one issue here. I will explain it right now. Let's double click on the scope and let's see what happens. Now here you need to be patient since the scope will take some time to load, and here it is. Okay, so here we need to increase the simulation time. So for example, let's say 60 or even 80 for example as simulation time, and let's run it again. And let's click on scope over here, and this exactly looks like our previously plotted step response in MATLAB. Good. And we can actually verify that. Now, if you go back to the MATLAB script, we can run the code again and we can compare the two plots. Here is the comparison of two plots. We can see that we did a good job. We can see that the settling time is approximately after 40 seconds, and that's exactly the same. That is, these two graphs are identical. Perfect. Let's continue. The next step is actually to implement our observer. That is, we need to implement this equation over here. Let's write this equation over here just in corners so we can later on refer to this equation in our Simulink model. So we have x hat dot is equal to a x hat plus bu plus L output of the system minus c x hat. And this is all we need to have to simulate this system in Simulink. Okay, so let's go back to the Simulink. Similarly to the case of our state space model, this equation can be written in the integral form. So let's do it. From this equation we have that x hat is an integral of ax hat plus, let me just erase this, plus bu plus L y minus c x hat, and over here the integration is performed with respect to dt. Okay, so we need to implement this equation. Let's look over here. Over here I'm going to double click and I will call this output y, since it's actually y. Now, next I will do the following. To make this graph less busy and more clear, I'm going to do this. Look at the magic. Bang. And then if you click here, you can click on create subsystem and bang. And here it is. You can call this as our plant. Okay, so what we can get out of the plant? We can get the output, let's just write it down y, and we can get the input. That's perfect. And let's change the locations of these two blocks, and let's continue with the observer development. The observer takes two inputs. It takes the output of the system and it takes the input of the system. And it has an integrator. First of all, let's create the integrator of our observer. Double click here and search the integrator. Here it is. Now click here, click on format, and let's rotate this thing like this. Perfect. The output of this integrator is actually our x hat. And then again, we need to form ax hat, then we need to form bu, then we need to form this, we need to add them together, we need to sum them up to get the x. So over here, the input to this integrator will be summation. So let's put summation. And over here, of course, let's rotate this. However, we need to sum three terms. So double click here and add another term. Add another plus here. And then we have three summations over here. Let's increase the size of this summation just for a second. Such that, oops, let me do Control Z. I didn't want to do this. Perfect. I just wanted to enlarge. Can I do it? No, I cannot do it. But it's good. No worries. Okay, so let's continue. The input is ax hat. So let's create ax hat. Over here, I'm going to double click and I'm searching for gain. Then this will be my A matrix, and this should be matrix multiplication. Then here x is coming in. Let's type it here. X hat actually. Let's put it like this. X hat coming in. Then what do we have over here? A as a matrix multiplying ax hat, and this goes here in one summation. So we can write here ax hat. Perfect. Let's continue. What do we have next? We have b multiplying u. So we need to take u and multiply b from the plant. No, not a big deal. So over here, let's add the gain. Good. This is the input u. We can again type it u here. It's u itself. Then double click here. This is b. And it's going to be over here matrix multiplication. Click OK. And over here we have another term. We have BU. Perfect. Now we need to create this third term, L multiplying y minus cx. So let's start with L. So again, gain. Here's the gain. Then rotate this. Bang. Put it here. Connect it here. And let's double click here and make sure that this is L. Make sure that this is matrix multiplication. Click OK. And let's just move this for a second. This will be L multiplying, let's put it like this. Just let's not put anything better because we have here parentheses and everything. So what is the input? The input is the difference of y minus cx hat. So let's do this. First of all, search for sum. Add the sum over here. Let's rotate the sum a little bit. Then one side is plus, one side is minus. So double click here and adjust the signs. One will be minus. Let's zoom out. Let's see what's happening here. So what is plus sign? We need to take the output of the system, as we can see here. So this will be the output, and this will be y, exactly y. And here it is. So what is this input with the negative port, or better to say with the negative sign? We need to take x hat and we need to multiply it by c. So let's do that. Click here. And over here, let's find the gain again. Here's the gain. Over here, you need to put c. And over here, matrix, which is very important. And double click here, make sure that we have matrix. So now, perfect. So let's see, C matrix. The input is x hat. So you can simply put here to make sure that it's x hat. And here it is. And this goes here. And that's it. Don't forget to connect this part. And that's it. Okay. Now, what do we need to plot over here? That's a very good. The output of our system is actually y, and y is equal to the first state of the system. Now, the same thing applies here. If we multiply x hat by c, we will have the output of the observer. That is, we will have x1 hat. So just let's, for the illustration purposes and to verify the performance of our observer, let's compare x1, that is the output of our system, and x1 hat, that is the output of our observer. The output of the observer, that is x1 hat, should track the output of our system. So let's verify that. Okay, to verify that, we need to add a scope over here. And over here, let me rotate this scope. I need to add the MUX or MUX. So click here and search MUX. And then again, rotate MUX. MUX is used to plot the two signals on the same scope. The first signal will be x1, or better to say, the output of our system. And the second signal will be actually C multiplying hat. So let's do that. Click here. Oops, I didn't do. Let's make it sure that it's here. And then move this thing here. Okay, perfect. Now, the observer over here starts from a certain initial condition, and in our case, the initial condition can be set by the initial condition of this integrator. The same thing applies for the system. So let's first of all adjust the initial conditions. Click here on a plant. Click here on this integrator to set the initial condition for the x. And over here, let's put the initial condition, for example, minus 0.1, 0.1, for example. Okay. And of course, there are some issues over here. Since we are dealing with a fourth order system, we need two additional initial conditions. So for example, 0 here and minus 0.1. So S1, 0 is minus 0.1, S1 dot 0 is 0.1, S2 is 0, and S2 dot is minus 0.1. Okay, that's it. Let's now go back to our plant. Let's go back by clicking here. You can always step in or step out. You can do it like this. And over here we need to specify the initial condition for our observer. Now, you don't know in practice what is the exact initial condition of the system, so we will do some guessing. For example, let's make a completely wrong guess. So 0.2, 0, minus 0.01, and let's make it over here 0.2. Okay, so the initial condition of our observer is completely different from the initial condition of our plant. And this is a realistic condition. What the observer should do, should correct for these uncertainties in initial condition and should be able to track our output. So click here and let's finally simulate the system. Click on simulation. Let's set, for example, the stop time to 100. Let's run and let's hope everything will be fine. Okay, let's see now here. Double click on scope and voila. Let's see what happened actually. This looks amazing. Wow, this is truly amazing. Let's see what happened. Wow, after approximately even 2 seconds, we are able to perfectly track the output of the system. That is, the x1 state of the observer becomes exactly x1 state of our system. This is amazing. This is truly amazing. And this means that the observer is actually working properly. Now you can play, of course, this graph. You can put a legend and you can confirm that it's actually not a gain tree, so we can adjust this. We can close this, and over here we can simply type that this is y hat, for example. Okay, and let's repeat this. Let's click here, and here it is. It looks really good, and you can see how quickly we are tracking the exact output of the system. Perfect. Now, over here, we are only showing the results for the first state. That is for x1, and we have seen that the observer is able to track x1. But how about the other states? So let's extract other states. So let's do that. Click over here on the plant, and over here, search for out, for the out port, and let's connect it over here. Now, this out over here will actually be the complete state vector of our system. And then go back, and over here you can see another output. Okay, now here we have to be very careful what we are plotting and how we are plotting. So let's do one trick over here. Let's make one block over here that will actually select a certain state from this vector, and over here from x hat we will do the same thing. So let's put here gain, and then let's rotate that gain. Let me just see for a second why. Oops, I didn't want this. Let me do here and search for gain. This is what I want. Click here, click on format, then rotate this. Okay, this will be the gain, and let's connect it over here. Good. Now, what this gain will do, we can actually multiply this signal over here, that is this vector, by a certain matrix, and we can extract the state that we wish. So click here, and let's specify, for example, 0, 1, 0, 0, such that we can extract a state x2. And let's make sure it's matrix, connect here, and let's do the same thing for x hat. So do here, search for gain, and then let's rotate it over here like this. Let's do this, connect it to the x hat, and then over here, click here, and let's extract the same 0, 1, 0, 0, and let's make sure that this is matrix. Perfect. Okay, then let's add the MUX block. Here it is. Rotate the MUX block. Click here and click here, and let's add scope. So click here and search for scope, and here it is. So let's now rotate the scope and let's see what happens. Okay, let's now simulate. To simulate, click here on simulation and click run. Perfect. Let's click on scope and let's see what will happen. Bang. Voila, here it is. Let's compare the results. Wow, we can see that we can track x2. And the legend will probably not help us a lot. Yes, they don't help us a lot. However, we can see that we are able to track the state x2 after approximately 3 seconds. In the first case, that is in the case of first scope, here it is. Let me just bring the second scope over here. Where is the second scope? Here it is. We are able to actually much faster track x1 compared to x2. As you can see, it's much faster. We can track x1 approximately after 1 second, but here it's around 2 seconds. This is because we are not directly observing x2. Let's now make checks for other states. Let's, for example, put here to be 0, 0, 1, 0, and over here 0, 0, 1, 0. That is, we are tracking x3. Let's simulate again. And let's see what happens. And voila, here it is. x3. We are able to track x3 after approximately 2 seconds. Perfect. Let's check the final state. Let's select here 0, 1. Okay. And over here 0, 1. And apply. Okay. Let's run again. Perfect. Bang. Here it is. We are also able to track the state x4, but again after 2 seconds. And that's it. Simple as that. Not too complex. To be honest, it requires some understanding of how observers work. It requires some coding and some Simulink skills. However, it's not difficult. Okay, that would be all for today. I hope that you like this video. If you like the videos I'm creating, please press the like and subscribe buttons. Thanks a lot and have a nice day.